This morning, we have an opportunity to explore one of the mysteries of space. That is black holes. And our guide is Dr. Charles Bailyn. Now, Dr. Bailyn is a professor of astronomy, and he's also a leader in an international effort in finding and identifying black holes. He does this by using a host of observational methods, which he'll be discussing today. As such, we are in excellent hands, as he will describe to us what exactly is a black hole and what are the tools for finding them. So we are certainly in for a real treat. So with that, I would say sit back, think about the heavens, and help me welcome Professor Bailyn to the podium.
Thanks, Anissa, and thank you for organizing this wonderful event. So I brought along this football with which I propose to demonstrate the basic scientific fact upon which the whole idea of a black hole is based. And that is simply that what goes up must come down. Now, like a lot of scientific facts, it's actually not quite that simple. There's the additional fact that the faster you throw it up, the longer it takes to come down. For those of you who are in danger of taking a high school or college physics course, I will tell you that there's a little equation associated with that fact, and you can figure out how long it will take for a football to come back down if you throw it up at a particular rate of speed. It's also true that the whole premise is actually wrong. We live in the space age, and so we send rocket ships up into space, and they don't come back down. So it isn't actually true that what goes up must come down. And in fact, if I were to take this football outside and throw it up into the air at a very high rate of speed, at, for example, 7 miles per second, very, very fast. My arm isn't quite up to it, but perhaps we could get some stronger person to do this and throw the football up at 7 miles per second. It would not come back down. It would escape from the Earth's gravitational field altogether. And any given object, the Earth, for example, has a speed with which, if you throw something up, it doesn't come back down. That speed is called the escape velocity, because if you throw something up faster than the escape velocity, it won't come back down. And again, there's a little equation associated with this. You can calculate the escape velocity for any given object. As I said, the Earth's escape velocity is 7 miles per second. The sun has a stronger gravitational field than the Earth. Its escape velocity is bigger, almost 100 miles per second. You can calculate the escape velocity of a human being. That's fun. It turns out it's about 1 millimeter per hour. And so, of course, that's really slow. I'm walking much faster than a millimeter per hour. I'm walking at about 1,000 millimeters per second here. And so as you go through your everyday life, you're moving around much faster than the escape velocity of the people around you. And that's why we don't feel each other's gravitational effect. And that, of course, is why people are not attracted to each other, at least... At least not by gravity, right? But of course, it is also true that as we move around in our ordinary lives, we're moving much slower than 7 miles per second, which is the Earth's escape velocity. And so we do feel a very strong effect from the Earth's gravitational field. Now, as I say, you can calculate these escape velocities for any given object. You can also figure out what kind of object you'd have to have a given escape velocity. And about 250 years ago, an otherwise obscure Englishman named John Mitchell did the calculation to figure out what kind of an object would it have to be to have an escape velocity faster than the speed of light. And so, again, he did a little calculation, and he discovered that in order to have a strong enough gravity, speed of light is very fast. It's 186,000 miles per second. So much faster than the escape velocity of the Earth or the escape velocity of the sun. And he discovered you'd have to have an incredibly strong gravitational field to have an escape velocity faster than the speed of light. But there's no reason that couldn't happen. You just have to have a very, very, very dense, heavy object. And he speculated a little bit about what such an object might look like. And he figured, look, if the gravitational field is so strong that light can't get off it, then no light comes to you from that object, and you can't see it, and it would be dark. And there's where he left it. And at the time, there was nothing particularly special about this. And in fact, that is basically the definition of a black hole. It's simply an object whose escape velocity is faster than the speed of light. He didn't use the word black hole. That wasn't coined until the 1960s, but that was the basic idea, and it was already explored 250 years ago. But as I say, nobody thought very much about it. It was just a sort of hypothetical, theoretical application of a set of equations that people used all the time. It wasn't until Einstein, exactly 100 years ago, came up with the theory of relativity that people realized that this was kind of a special situation. And the reason it was special is because the speed of light turns out to be a very, very special velocity. And in particular, it turns out that nothing goes faster than light. You cannot go faster than the speed of light. It's the ultimate speed limit. So if you have something whose escape velocity is greater than the speed of light, light can't come off it, but nothing else can come off it either. No information of any kind and no effect of any kind can come from an object whose escape velocity is greater than the speed of light and make it back to us, because the gravity is so strong that anything that tries to get off it will fail and will fall back down. Now, Einstein realized, and Einstein and the other people studying relativity realized that this had a very particular effect. This meant that if nothing can communicate from such an object to the outside world, then in a certain sense that object isn't part of our universe. What do we mean by being part of the universe? Being part of the universe means something somewhere that might have possibly an effect on something that might have an effect on us. The most distant stars, well, we can see them. Their light comes to us. And even if we can't see them, then maybe something can see them that we can see. And so there would be some way that information about them could conceivably come to us. And an object whose escape velocity is greater than the speed of light isn't like that. Nothing can come off of that. No information, no light, no radiation, nothing of any kind can come off it. So in a certain sense, it's not part of our universe. And in fact, you can think of the universe as not being a big thing, but a big thing with holes in it, sort of like Swiss cheese. And so inside are these little pieces cut out of our universe that don't have any effect on us at all. Sort of a bizarre thought. And so the whole idea of what a black hole is it's simply a big imaginary circle in space. And the properties of that circle is that it's a sphere, really. On that sphere is where the escape velocity is equal to the speed of light. And then there's some really dense thing inside here. And this is called the event horizon, because any event that happens inside it cannot communicate in any way with anything outside it. And the radius of the event horizon is given the name Schwarzschild radius. Schwarzschild was a scientist who worked on relativity and then was killed in World War I, but not before he calculated what this Schwarzschild radius might be. And inside the event horizon, you're, in this sort of philosophical sense, not part of our universe. And if you nevertheless take the standard equations and ask, well, what's going on inside here, you get very, very strange answers. For example, it turns out to be the case that inside the event horizon, space and time are reversed. Now, what could that possibly mean? Well, think about what time is like. We're all moving forward in time. We're moving at the rate of 1 day per day. And there's not a lot you can do about that, unfortunately. If you have, a jet engine or something and you turn it on and you rush off, you can't slow down how fast you're moving in time. You're always moving forward, and you're always moving at the rate of a day per day. On the other hand, if you turn on your jet engine or any other energy source, like the chemicals in my body, you can move around in space. I'm doing it right now. I'm walking back and forth. I can walk forward and back. I can jump up and down, all by expending energy. But you can't do that with time. Now, inside the event horizon, it's the other way around. You always go in the same direction in space. You fall toward the middle. And you will fall to the exact point in the middle, which is called a singularity, after some amount of time. And anything inside the event horizon will fall straight toward the center. And if you turn on a jet engine or other kind of energy source, you don't change that. You don't change that because it turns out, as Anissa pointed out, E equals mc squared. And so the amount of energy that you use to try and slow yourself down actually gives you more mass. That mass just makes the gravitational force faster, and it compensates, and you fall straight down toward the center. So you're going in one direction at a given speed in space all the time. But if you turn on that energy source, it turns out it has to have an effect, and it moves you around in time. This is why the science fiction writers like black holes so much, or one of the reasons. It's because it gives you a scientifically certified time machine, and that's important for the plot of a lot of science fiction novels. What they usually forget to tell you is that there's this event horizon on the outside, and so if you move around in time, you don't get to come back and enjoy it. And so it doesn't actually do you any good. There are all sorts of other things, crazy things that happen inside the event horizon. The theoretical physicists worry about this a lot. The science fiction writers, as I mentioned, worry about this a lot. But I'm neither one of those things. I'm an observational astronomer, and at this point you should be very concerned. And the reason you should be concerned is that my first two slides contradict each other completely. Remember what the title of the talk was? How to see a black hole. I've now just spent the past 10 minutes explaining to you why that's totally impossible, right? Because the gravitational field here is so strong that light isn't going to come off. Nothing's going to come off. There's no possible way to see this. It's not even part of our universe. And yet, I propose to spend a whole hour explaining to you how to see a black hole. And that's basically the topic of my talk, how we know that these things really exist, how we can study them, and how you can actually observe something that's intrinsically impossible to see. All right. So the first step along the way is just to say that it is the case that for over 70 years, we've known that black holes should exist. They should exist because there are certain kinds of stars which are going to inevitably end their lives in the form of black holes. And to understand this, you have to first understand why it is that every star isn't a black hole. If you think about it, a star like the sun have enormous amounts of gravity. They pull things in really hard. And they also don't have solid surfaces. They're not like the Earth. They're made up of gas. And so why doesn't every atom in every piece of gas in a star simply sink to the center of that star because of the star's gravitational force? And there's a one-word answer to that question, and that word is pressure. Again, that's one of these scientific concepts that seems simple when you name it, but when you think about it a little bit more, it gets more and more complicated. Think about a balloon. When you blow up a balloon, the elastic in the balloon is trying to make it smaller. But something is preventing it, and the reason it's preventing it is that there's a little more air, maybe a little bit hotter inside the balloon than there is outside. And so the air pressure inside the balloon is greater than the air pressure outside the balloon, and that air pressure pushes outward against the force of the elastic pushing in. And basically that's the exact same way stars work. Gravity pulls in, pressure pushes out, and at every point in the middle of a star like the sun, those two forces balance, and so the sun can happily sit there and shine for 5 billion years without getting particularly smaller or bigger. Now, in order to make this work, it turns out that in order to have the right amount of pressure, the middle of the sun has to be hotter than the outer part of the sun. That's where the extra pressure comes from. And we know why that is. It's because there's a big energy source down in the middle of the sun. There's hydrogen fusion. That's how the sun shines. It's sort of a big hydrogen bomb. And so there's all this energy being created in the middle. That keeps the center hot. That keeps the pressure high. And that opposes the force of gravity. And then gradually that radiation will leak out, and that's why the sun shines. But there's a problem with this in the long run, which is that eventually you run out of hydrogen. You can, it turns out, fuse other elements, but eventually you run out of all nuclear fuel in the middle of the star. And then something has to happen because there's not enough pressure to hold it up, and things start to collapse. So you end up with no fuel left, no pressure. The star, not no pressure, but not enough pressure to counteract gravity. The star starts to collapse. So here's a smaller star. And eventually that process can stop because when a star becomes very, very dense, it turns out there's a new kind of pressure that comes in that isn't dependent on temperature and therefore doesn't need to have nuclear fusion going on to hold up the star. But that only happens after it's contracted and become very, very dense. So the end of the life of a star, the endpoints of stellar evolution, one of them is as what we call a white dwarf. These are very common kinds of stars. You get about the mass of the sun in a volume about the size of the Earth. The Earth is much smaller than the sun, so that means this is really dense stuff. Imagine stuff that's about a ton per cubic centimeter. So very, very dense, far denser than any kind of ordinary material. And then you have a whole star that's that dense. These are white dwarfs, and as I say, they're actually pretty common stars because every star, like the sun, is going to end up as a white dwarf after it runs out of fuel. So 5 billion years from now, the sun will be a white dwarf, held up by this other kind of pressure, very, very dense, crushed down to the size of the Earth. Now, it turned out, and this is what was discovered 70 years ago, that you can't be a white dwarf if you're more than 1.4 times the mass of the sun. Because if you're more than 1.4 times the mass of the sun, the gravitational force will beat even this new kind of pressure, and the collapse will continue. And this was discovered by a man named Chandrasekhar, one of the great astrophysicists of the 20th century. I think I have a picture of him here. There's Chandra, as he was known. And this is him as a student at Cambridge University in England. And he was a student when he made this great discovery that you couldn't have a white dwarf more than 1.4 times the mass of the sun. And he had an unfortunate experience. He went to explain his great new discovery. As I said, he was a student to the Royal Astronomical Society, which is a big deal organization in England where the astrophysicists get together and tell each other what's going on. And so he explained his whole idea. And then his teacher, his thesis advisor, a man named Sir Arthur Eddington, very, very famous guy who was supposed to be, at the time, the only guy in the world who really understood relativity except for Einstein. So his teacher then got up and denounced him. Very unfortunate occurrence for young Chandra. And everybody believed the famous teacher. They didn't believe Chandra, but Chandra was right. And 50 years later, he got the Nobel Prize for it. But there was a kind of delay before people accepted this result. And here's what Eddington said. He said, there ought to be a law of nature to prevent stars from behaving in this foolish manner. And so Eddington was convinced that this idea, which Eddington was very smart, he realized that if this was true, it meant that black holes or something like them would have to exist. And he was very disturbed by that, and he figured there had to be some law that prevented such a crazy thing from happening. Now, this is a very, very unscientific thing to say. Who are we, or who is even Sir Arthur Eddington, to say what nature can and cannot do? And it's a useful thing to remember, perhaps, that if Eddington had believed his student instead of his gut feeling, then we would have started studying black holes in the 1930s instead of the 1960s, and we'd be 30 years further advanced. A lesson to students and teachers alike, perhaps. It turns out there is another kind of pressure. They didn't know that at the time. What happens if white dwarfs continue to collapse is that you know that atoms are made up of electrons and protons and neutrons. And what happens is the electrons and the protons get all squished together and turned into neutrons. And then you have basically the star turns into one big atom, a single atom with billions and billions and billions of neutrons and no protons and no electrons. So it's an atom made up entirely of neutrons, and you can get the mass of the star crushed down into a volume, the size of Yale University, about 10 kilometers across. And now you've got something that's 100 million tons per cubic centimeter. Incredibly dense stuff. These things, and then a different kind of pressure again comes in. Whoops. Hello. Let's cancel that. All the subatomic particles crush together to make a single atomic nucleus. And these things are called neutron stars. And they, again, are known to exist. They're observable in the form of pulsars. They were discovered in the 1960s, and this is what prompted people to start thinking once again about the possibility of black holes. Now, there's a problem with neutron stars, which is they have the weird property that the more massive they are, the smaller they become. And it turns out that if they're more massive than 3 times the mass of the sun, they fit inside their own event horizon. So this is an object that lives inside the event horizon, but anything that lives inside an event horizon is a black hole. It doesn't matter what it is. It doesn't matter if it's neutrons or feathers or anything else. If it's smaller than if it's inside its own event horizon, then you've got yourself a black hole. So if the mass is greater than 3 times the mass of the sun, then the neutron star fits inside its event horizon and therefore must be a black hole. So just to summarize, if you're less than 1.4 times the mass of the sun, you end up as a white dwarf. If you're less than 3 solar masses, you can end up as a neutron star. If it's more than 3 solar masses left at the end of the lifetime of a star, then that object, once its nuclear fuel is all exhausted and it doesn't have the standard kind of pressure anymore, has to collapse to a black hole. Now, you'll notice the asterisk. I've said a couple times already that these kinds of broad scientific statements, it has to be a black hole, tend to be more complicated than you think at first. And there's an exception. There's a way out of this being a black hole, which is that the Schwarzschild radius, the whole idea, remember, is that the thing is smaller than its event horizon inside its own Schwarzschild radius. The Schwarzschild radius calculation depends on general relativity being a correct theory. So the alternative is that Einstein could be wrong. And in a way, this is one of the reasons it's nice to work on these things, because either it's a black hole, which is pretty exciting, or Einstein's theory, the 100th anniversary of which we are celebrating this year, might be incorrect, and there might be some better theory that one would have to figure out, which would be even more exciting. So either way, a compact object at the end of the life of a star, more than 3 solar masses, is kind of a fun thing. So the trick is, where do you find these compact objects, and how can you figure out how much they weigh? I like to look at objects like this. This is a so-called X-ray binary. This is a double star. Turns out most stars come in pairs. Our sun is an exception. It doesn't have a companion star. Good for us. It would be a problem in terms of the seasons, for example, if Jupiter were actually a star. And so here's a double star. This is an ordinary star, more or less like, I should say this is an artist's conception. This is not a picture taken at a telescope. This is an ordinary star, a lot like the sun, except it has this somewhat weird shape. And what this shape is that's basically the same as the tides. That's a big lump that's pulled up on one side of the star. And the reason it is because the other star, which is down in the middle here, so small you can't see it, is actually more massive than this star is. It's one of these compact objects I was talking about before, and it's got so much gravity that it's actually pulling stuff off the surface of the other star and down onto itself. And what happens to this stuff is there's a gas stream here, and then it goes into this disk, and it goes into orbit around the thing in the middle, and gradually, through friction, it spirals in, going faster and faster, and falls down on top of a tiny little star down there so small you can't see it. As the material spirals in, the reason it spirals in is because there's a lot of gas, there's a lot of friction. Friction, of course, makes heat, and it gets hotter and hotter and hotter. And this disk, a so-called accretion disk, is much hotter than the star actually is, because the gravitational force of the thing it's falling on is so big. Down in the middle there, these things get so hot that they don't emit ordinary light, they emit X-rays. And these things turn out to be the brightest sources of X-rays in the sky. X-ray astronomy is kind of a newfangled science. X-rays don't make it through the atmosphere. So you can't observe X-rays from an observatory on the surface of the Earth because the X-rays don't make it. It's good for us that X-rays don't make it through the atmosphere. The sun generates X-rays. We would all get radiation sickness if there weren't the atmosphere. It's bad for X-ray astronomers because it makes it awkward to build an X-ray observatory. You can, however, put an X-ray observatory into orbit. This has now been done. The Hubble Space Telescope is the most famous space telescope, but it's not the only one, and some of the most productive ones are these X-ray observatories. And if you look at the sky in X-rays from out beyond the atmosphere, you see many bright sources of X-rays, and the brightest of them all are these X-ray binaries. And what you're seeing is the central part of this accretion disk. Now, when you see that many X-rays, you know that the thing that's accreting the gas has to be a compact object. And the reason you know that is if it was an ordinary star, the gas wouldn't build up enough energy to create all these X-rays, because X-rays are very energetic kind of radiation. So it has to be a compact object. So the question is, can you figure out how much it weighs? And it turns out that this can be done. And what you do is you watch the other star, the ordinary star, as it orbits around this unseen object. And the faster the orbit goes, the more massive the thing it's orbiting around has to be. If the object is pulling you really hard, then you have to move really fast to stay in orbit. So if you can measure the speed where it goes around in its orbit, you can determine the mass of the thing it's going around. Now, it turns out that measuring speeds, measuring velocity, is something we know how to do. This is done using the so-called Doppler shift. So let me briefly explain that, and then I'll demonstrate it here. What happens is, supposing you've got something that's emitting light waves, and it's moving. It's coming towards me here. So this light bulb's going to move. And then what happens is, as it moves, it emits light waves. The light waves travel outwards. They travel outwards from where they were emitted. But each time a light wave is emitted, the light bulb's in a different place. So you're going to get a bunch of expanding waves, but each of them will be centered on a slightly different place. So let me show you how this works. Here's the light bulb. It's moving toward me. And at each of these dots, it emits a wave, and the wave travels outward. So when it was at the purple point, it emitted the purple wave, which has traveled the furthest out, but it's centered on the purple dot. And each one of these dots, it emitted another wave of the color of the dot, so you can see it here. And for example, this green one has ended up here. And the centers of all these outward going waves have changed because the thing is moving. So now look what happened. If I'm standing here, the waves are coming towards me, and they're very close together. So the wavelength that I observe is shorter than it otherwise would be. But if I stood over here where the object was going away from me, I'd see these waves much, much further apart. So the wavelength changes depending on whether the object is coming towards you or moving away from you. And if it's coming towards you, the wavelengths get shorter. If it's going away from you, the wavelengths get longer. Now, we can perceive the wavelengths. I'm going to give you an example with sound waves in just a minute. Sound waves, the way it works is short wavelengths are high-pitched noises. Beep, something like that. Long wavelengths are low-pitched noises. Ooh. Things of that nature. And so if something is coming towards you, you'll hear it at a higher pitch than you thought. This is the so-called ambulance effect. I don't know if you've noticed this with sirens coming down the street, and a siren's coming down the street at you this way, and when it passes you and starts going away from you instead of coming towards you, the pitch drops. So you hear boo as the thing goes past you on the street. So I have a demonstration. Let's see. Let's see if I can get this to work. There's a noise, yeah? And it's a high-pitched noise. And what I'm going to do is I'm going to put this thing in motion. And I'm going to swing it around my head. And what ought to happen is that when it comes towards you, it ought to sound a higher pitch than when it's going away from you. Is it working? Cool. I can't tell. Do you understand why I can't tell? I'm in the middle. It's not coming toward, I'm swinging it around. It's not coming toward me or going away from me. And so I couldn't tell from where I was sitting. It was exactly the same pitch the whole time as it went around because it's not coming toward you or away from you. Let's try an experiment. I don't know whether this will work, but that's the nature of an experiment. everybody put your hand up, but really quickly, up and down. Yeah, up and down. Good. Here's what I want to try and do. When you hear, okay, you can stop for a sec. When you hear the thing at its highest pitch, the highest pitch, put your hand up really quickly. But only when you hear the thing when I start swinging it around when it's really high pitched. Let's see if this works. Yeah, it's okay. There's a tendency for it to start here and move that way. That's because the thing's going around this way, and you guys hear it first, and then you do. If I swing it the other way, yeah, more or less. As I say, I can't tell, right, because I'm standing in the middle, and I don't hear the pitch change at all. So that's how it works with sound waves. Light waves work a little differently because, of course, you can't hear them with your ears. You see them with your eyes. And short wavelengths are bluer than long wavelengths. That's the difference between colors. Blue light is short wavelength light. Red light is long wavelength light. So now think what happens if you look at an object that is in an orbit around some other object. So this object is going around in circles, and sometimes it's here. I'll use the football. Sometimes it's coming towards you, and sometimes it's going away from you. And when it's coming towards you, it looks a little bluer, and when it's going away from you, it looks a little redder. So if you observe its color over time, you can see first it looks blue when it comes towards you, then it looks red, then it looks blue again, and it goes through these cycles. And so you can measure these things if you plot what's called radial velocity. Radial velocity means how fast it's either coming towards you or coming away from you. Usually the way it's set up is negative numbers are coming towards you, positive numbers are going away from you. And you plot that, you measure that, and you plot it as a function of time. It comes towards you, it goes away from you, comes towards you, goes away from you. And you can immediately figure out two things from making this observation. One is the orbital period, how long it takes to go around one orbit. The orbital period of the Earth around the Sun is a year. The orbital period of the Moon around the Earth is a month. But you can also figure out how fast it's going. It's not quite how fast it's going. It's a minimum speed because, you know, it could be going this way. It could be going sideways where it never comes towards you or away from you. And so what you measure with radial velocity is less than, might be the true speed if it's going around like this, or it could be less than the true speed if it's going around this way. So it's a minimum velocity. So you measure the minimum velocity, measure the orbital period, and from those two things, you can figure out the mass of the other object. That's why this is so great, because you can figure out the mass of something you're not looking at. You're looking at the thing that's doing the orbit, and you're figuring out the mass of the thing it's orbiting around. So you observe the companion star, and you figure out what the mass of the compact object in the middle of the accretion disk is. There's a technical problem. Turns out the accretion disk is so bright that you can't see the other star. All that energy, you know. But it also turns out that there's a way that nature has provided of turning off the accretion disk. What happens is that a lot of these systems are so-called transients, where you get a little piece of accretion. The compact object bites a small piece off its companion star. That piece of mass falls down. It lights up. You see X-rays, all kinds of fireworks. And then it finishes eating that piece of the star, and then it doesn't eat anymore for decades. And so then there are long periods where all you see is the companion star. It just looks like any other ordinary star, except that you know that it isn't because you used to see all these X-rays. So here's how you find a black hole. Simple 5-step process. You wait for a new X-ray source to be identified. That's when it decides to eat a piece of its companion. You figure out which star in the sky is associated with all those X-rays. You wait. You wait some more because you can't do the next step until the outburst has stopped. And then when the outburst is finally over, you observe this radial velocity. You observe the Doppler shift. You figure out how fast the star you can see is going. And then you determine a minimum mass. And if that minimum mass is more than 3 solar masses, you win. That is to say, you have discovered a black hole. Because you know it's a compact object, or they wouldn't have been the X-rays, and you've now measured its mass to be more than 3 times the mass of the sun. So I've done this a few times. And I thought I'd tell you about the very first time this happened. It started with this, this communication here. This is a so-called X-ray telegram, X-ray astronomy telegram. What they do is there are things going on in the sky all the time. New comets, supernovae, novae, all kinds of exciting things happen. And you need a way of telling people at other observatories that something exciting has happened. If you wait 2 years to publish your result, it will be gone. And so that isn't good. And so they had this system set up of telegrams where you would send in your cool new result. Amateurs could do this too. You send in your cool new result to somewhere in, actually it's in Cambridge, Massachusetts as it happens. And you send it in and they circulate it to all the observatories everywhere in the world. Now, of course, it's done by email, but at the time it was done by telegrams. So here is an astronomical telegram. And there's a whole bunch of astro jargon down here. Pay no attention to it. The title tells you everything you need to know, which is that there is now, these people are announcing that there is an X-ray transient, a new source of X-rays never before seen, in the constellation of Musca, Musca the Fly. You've probably never heard of the constellation of Musca the Fly. It's quite obscure for two reasons. First of all, it's in the southern hemisphere. You can't see it from here. Second of all, it's a pretty pathetic excuse for a constellation. It's got, you know, they had to call that part of the sky something, but there really isn't much there. There's one pathetic fourth magnitude star. That's why they call it the Fly, okay? And you can picture how this looks on the little maps. There's this one star, and they put wings on it and call it a fly. But nevertheless, this constellation is now one of my favorites because it contains this object. So big new source of X-rays in Musca in the southern hemisphere sky. So here's the picture I started with. This is an observatory in Chile in the southern hemisphere. This big telescope dome, this is actually how the sky looks down there. It's amazing. This is the center of the galaxy. This is the Milky Way. That's one of the Magellanic Clouds, the closest galaxies to our own. And again, that's something you can only see in the south. It's very, very spectacular. And this was at the time, in the early 1990s, the most powerful telescope in the southern hemisphere. Just to give you a sense of scale, that's the door, that down there. So it's a very big building. It has a very big telescope in it. I have some. Here's the telescope itself. The way it works is this. In here is a big mirror. And the light comes, this is the domer, and the light comes in from here. It bounces off the mirror that you can't see there. I'll show you the mirror in a minute. Bounces up to another mirror here and bounces back down to here where there's some kind of camera in this cage. It used to be, when they first built the telescope and they were using photographic plates to record the data, that the astronomer would ride around in this cage all night long. So that you could change the photographic plates and things. By now, fortunately, there's electronics down there, and there's a little wire coming off the back here that leads to a control room where you can sit where it's warm and it's not dark, and you don't have to ride around in the dark for 8 hours anymore. But very big, and the heart of it is this big mirror in the middle here, which is a 4-meter mirror. So it's 13 feet across, perfectly constructed mirror to reflect the light. And so basically what happens is you get the same amount of light you would get if your eye was 13 feet across. That's how a telescope works. So it collects lots and lots of light. Here's the mirror they took it out to repair. This is the mirror back here. It's got a hole in the middle because the light has to come back down through and go into that cage. They've taken the shiny stuff off the mirror. It's just a piece of glass now, and they're working on it. And the mirror sits on top of this apparatus here, and these things which it sits on sort of push up on the bottom to keep it in the right shape, because as you move the mirror around, glass is actually a little bit of a liquid, and it flows. And so in order to keep the right prescription on this mirror, you have to push on the back end. And so these are these little pushers. And they're going to polish that up, put it back on here, and put the whole thing back in the telescope in a little while. Anyway, so that's the great 4-meter mirror. But I'm actually more interested in this telescope here in the foreground, because this one happens to be owned by Yale. It's a much smaller telescope, although it works on the same principles as this one. And at the time, shortly after the announcement of these X-rays, I was down in Chile doing some observing, and I decided that the new X-ray source was actually much more interesting than the thing that I thought I was going to observe when I went down there. And so I changed my mind and did this other thing. And here's my telegram. That's me. And then again, a whole bunch of astro jargon. Pay no attention to it. The key thing is that we found the star that was emitting all the X-rays, and it changed its brightness every 10.5 hours. And what the outburst was still going on, so we couldn't do the radial velocity curve or anything, but what we think was happening was most of the light we were seeing was from the accretion disk, but once per orbit, the ordinary star got in the way, and there was an eclipse, and there was a dip in the light. And so you could figure out what the orbital period was. So I had half the information you need to make this measurement. But until the outburst was over, you couldn't get the radial velocities. You needed a bigger telescope anyway, so we applied for some time on the Great Big Telescope for the following year to try and make this radial velocity measurement. And we traveled down. This is where the observatory is. It's a little north of Santiago in Chile. Chile is this strange one-dimensional country. And up here, but it has these great mountains in the desert. That's where you want to put your telescope. And so here up in the Andes, here is where the Cerro Tololo Inter-American Observatory is. And we traveled down there. We had 3 nights of observing to make this observation. And what we knew was the orbital period was 10.5 hours. And so we realized, we did a little calculation, that if the difference between how fast the star was going when it was coming towards you and how fast it was going when it was going away from you was 800 kilometers a second or more, then the mass would be 3 times the mass of the sun, and it would turn out to be a black hole. So here's what happened. We went down there. The first night, it rained. Now, of course, you put your observatory in places where that's not supposed to happen, but sometimes it does. And it's an occupational hazard of astronomy that sometimes you get rain. And this is bad because they don't give you a rain check. You just lose your night of observing. The next night, so we had 3 nights. The second night, it hailed. I don't know if you've ever been inside a hollow 6-story high steel building with golf ball-sized hailstones raining down on it. That was exciting, but it didn't get us a lot of science done. So now we were worried because we'd lost 2 of our 3 nights. And, you know, they give you these places to sleep, little dormitories, because you have to sleep in the daytime. And so they're light tight and sound tight. Nothing gets into them. There's these little boxes. And you wake up in the late afternoon at 4:30 in the afternoon, having gone to sleep at dawn, and you open the shutter. And there's this moment where you look out at the sky and you think, am I going to be able to accomplish anything tonight? And fortunately, on the afternoon of the 3rd night, it turned out, fortunately for us, that the storm had passed and it was clear. So we were going to have 1 night of observing. So what I'm going to show you is what we observed on that 1 night. Here are hours in time. 10 hours between sunset and sunrise. And here's the radial velocity of this thing. So remember, minus numbers means it's coming towards you. Positive numbers means it's going away from you. This is in kilometers a second. And if the difference between when it's coming towards us as fast as it can and when it's going away from us as fast as it can is more than 800 in these units, then it has to be a black hole. So here was the first observation. This is already very good news. It's coming towards us at 250 kilometers a second. And things don't usually go that fast. And so the only excuse for that's faster than the escape velocity of the galaxy. And so ordinarily stars don't go that fast, and so that shows that it's in a very tight binary orbit with something else. So the basic idea is more or less correct. And then we observed a few more points. And by now, it's perfectly clear that it has to be a binary star because the first observation, it's coming towards us at 250 kilometers a second. Now it's going away from us at 200 kilometers a second. So it's gone around a large fraction. In 2 hours we've been observing it, it's gone around a big fraction of its orbit. So then more points were observed. And now it's midnight, and now we're pretty happy because it's going away from us at over 400 kilometers per second. Now, we think it's a 10.5-hour orbit, so 5 hours ago, which is down here somewhere, it was probably going towards us at 400 kilometers a second, but we couldn't observe it then because the sun was still up. So we haven't quite got the proof, but it sure looks promising. And so we were very enthusiastic, but, you know, things happen. At this point, there was a small earthquake. Chile is prone to this kind of thing, and earthquakes do bad things to precision-aligned optics. And so we kind of sobered up fast, put the telescope back together again. But it is true that the next point is discordant. It's sort of got out of whack. And then there's an hour-long gap, which we don't actually explain in the paper we subsequently published, while we sort of straightened everything out and got it working again. And now it's clearly what's happened is it was going away from us as fast as it can, and now it's kind of in this part of its orbit here. And we observed more points for the rest of the evening, and things seem to be going well. And now it was sort of almost back to where it started. So it started coming towards us, then it went away from us for a while, now it's coming towards us again. And we really wanted one more point, because we figured it'll be down here, and that's the thing we need to prove that it's 800 kilometers a second different from this to up in here. And, this point we kind of throw out, because that's the earthquake point. But there's a problem, which is, objects rise in the east and they set in the west. And so as we've been watching this for almost 10 hours now, the object's gone up, come down, and now it's setting into the west. And this telescope is having to point closer and closer to horizontal to follow it. Now, remember what that mirror looked like. It's not bolted down. It can't be bolted down because bolts change their size a little bit when the temperature changes. And so if you bolt the thing down, it'll squeeze on the mirror and bend it out of shape. So it just sits on top of those pads. So now this mirror is sitting on top of the pads, and the telescope's doing this. And there's a tipping point that's going to happen at some point, and the mirror is going to fall out and break on the floor. It's very much more than 7 years bad luck if you break the primary mirror of the largest and most powerful telescope in the southern hemisphere. So they actually, it's interesting, they don't even let the astronomers move the telescope because we'll screw it up. So they have these technicians whose job it is to keep the astronomers in line. And they're the only ones who are actually allowed to move the telescope. So right around here, our techie is telling us, professors, you may not continue this set of observations. You are endangering the telescope. This is very, very bad. You have to stop now. And we said, as scientists do, no, in the interest of science, we need one more point down here. And we had this big argument, and at a certain point, the techie picks up the phone and starts, this is 5 in the morning, right? Starts dialing the home phone number of the observatory director. Another thing that's really bad is to wake up the observatory director at 5 in the morning. So at this point, we said, all right, we give, it's over. But of course, we were taking data during the argument. The argument had gone on long enough for us to get the final data point that we needed, and this is the clinching one. It shows that and though over breakfast we figured out exactly what the best fit sine curve to this was, and here's our telegram. Again, a bunch of astro jargon. The value of the mass function, 3.1 times the mass of the sun, provides dynamical evidence, dynamical meaning from the motions of the stars, that the primary, the more massive object in the system, is a black hole. Now, those of you who are scientifically inclined will notice plus or minus 0.5 here. And let me just remind you that this is a minimum mass, and it turns out there was other evidence that the angle of the orbit was such that the mass is actually up around 7. But this is an absolute minimum to what it could possibly be. And so then we tried to publish our paper. The paper was entitled something like Evidence for the Existence of a Black Hole in the Constellation of Musca. We sent it into Nature. The editor of Nature didn't like this title. The editor of Nature said, now, it's an extraordinary claim to claim something's a black hole. You need extraordinarily powerful evidence. And you haven't taken into account the fact that Einstein might be wrong. And we said, come on. We get to assume that Einstein is correct, Oh, no. So we compromise. We don't call these things black holes. We call them dynamically confirmed black hole candidates. And here they all are. There are the one I've been talking about, the one in Musca, is a small system, short orbital period, 10.5 hours. These are to scale. This is the Sun and the orbit of Mercury. This is the biggest of them. Has the longest orbit, 30 days. And by now, 10 years later, there are over a dozen of these things, dynamically confirmed black hole candidates. Interestingly, there's also a bunch of things that turned out not to be black holes, that turned out to be neutron stars instead. And that's great because now finally you can do science, because you've got, you know how science is supposed to work, right? You're supposed to have controlled experiments, all this kind of stuff. Very difficult to do in astronomy. How would you do a controlled experiment in astronomy? You stick a ball of hydrogen the size of the sun and another ball of helium the size of the sun, and you watch them for 10 billion years. Hard to do. But in this case, you can actually start to do experimental science, because you've got one group of objects that are supposed to be black holes and another group of objects that are otherwise extremely similar that are going to be neutron stars. And so you can reverse the question. The way we've set this whole thing up, we said, you know, Einstein must be right, so if Einstein's right, then these things are black holes. If general relativity applies, then these things are black holes. But you can ask the other question. You could say, if these things turn out not to be black holes, then Einstein is wrong. And that's very exciting, because then you got to come up with a new theory. So you better take these black holes and look for expected behavior of black holes that you expect not to see in the neutron stars. Here's an example. So ask the question, do event horizons exist? That's the basic idea of a black hole, is that they don't have a surface, they have an event horizon. So let's take a neutron star and a black hole, and we'll dump gas on it. Well, just pour stuff on top of it. That's what's happening in these binary stars. They're pulling material off the other star. The stuff is coming down. And one of two things will happen. If it's a neutron star, it'll hit the surface. Now, if you drop something onto a surface, let me drop something onto a surface. Let's see here. All right. I'm going to drop this onto the floor. It's a piece of chalk. And something will happen. What do you think will happen to the chalk? Yeah? It'll break. It'll break for sure. Let's try. Boom. 8 different pieces of chalk. Why? Why did it break? Why did it break? It broke because as it dropped down, it got faster and faster. And then when it hit the floor, it couldn't go anymore. And so it had pulled together a lot of energy because it was moving fast. When it hits the floor, it can't move anymore. That energy has to do something else. The energy broke the chalk apart. And so if gas is falling, oh, I'm in the way of the neutron star. All right. If gas is falling onto the neutron star and it hits the surface and stops, the energy that it carried has to do something. It can't break the neutron star. The neutron star is too tough for that. And so what it does instead is it heats up the surface of the neutron star, and the neutron star starts to glow, and it gets so hot that it glows in X-rays. And so you get extra X-rays, not just from the accretion disk, but also from the surface layer, the so-called boundary layer, because the energy that all this gas had, it turns into radiation. Now, what happens if you drop stuff on a black hole? If that had been an event horizon instead of a surface, the chalk wouldn't have broken, because there was no moment at which the energy would have had to turn into some other form. Instead, what happens is it just falls right through, and the energy, E equals mc squared again, the energy contributes to the total mass of the black hole. The black hole doesn't care whether its mass comes in the form of what we think of as mass or in some other form like energy. And so there's no boundary layer X-rays. And so you make a very clear prediction. If event horizons exist, then the dynamically confirmed black hole candidates ought to be less bright than the neutron stars, because the neutron stars will have this extra source of X-rays. So here's data from the Chandra X-ray Observatory. And what they've done is they've plotted the luminosity, how bright in X-rays it is, against the orbital period. And these dark circles, forget about the extra circle. That's just the data that were presented in the particular paper. But these black circles are all black holes. Dynamically confirmed black hole candidates. And these open circles are all neutron stars. And the important thing is that this is a so-called logarithmic plot here. From this tick mark to that tick mark is a factor of 100. So something that's here is 100 times brighter than something's here. And so you can see you can drive a truck through this, right? The neutron stars are systematically 100 times brighter than the black holes are. And so this suggests that it really is true that these things that are more than 3 times the mass of the sun and so on, really don't have surfaces. They really do have event horizons through which material can pass out of our atmosphere, out of our universe even. So here's where we stand. This is the situation now. We now have 14 dynamically confirmed black hole candidates. I should also say something I haven't discussed at all in this talk. There is now equally good evidence for what's called supermassive black holes. These are things that are not a few times the mass of the sun, but billions of times the mass of the sun, and sit in the centers of galaxies. And there's now equally good evidence for these supermassive black holes. And when you look at the detailed behavior of these things, you know, how bright they are, what kind of radiation they give off, it does seem to be in accord with with expectations, in particular with the expectation that event horizons exist. And so now, as I said just a minute ago, we now, you know, 10 years ago, it was exciting to find something that probably was a black hole. So we did that a bunch of times, but it's only after you've found a bunch of these things that you can really start to try and understand them. Because the way you try and understand these things is not just to discover them, but to compare them to each other and to compare them with other kinds of objects to try and figure out really how they work. And that's the process that we're now in a position to really start. And I'll just close by putting up this, this website, which is a place that I've written down a whole bunch of stuff about black holes. So if you want to get more information, that's a good place to start. So thank you, and I'm happy to answer any questions you might have.